Hey guys, welcome back to the course. I hope you guys enjoyed the previous section about transfer learning, a powerful technique that can save a lot of time and can provide amazing results in a variety of applications. One of these applications is commonly referred to as style transfer. Style transfer deals with the process of differentiating between image content and image style, where image content relates more heavily to the objects in the image and the specific layout of these objects in the given image, while image style refers to the specific style within an image. At a general level, this can refer to basic components of the image such as color and texture. This can also include more specific features such as the style of paint strokes or the style of painting technique used. The aim of style transfer is to combine the contents of an image with the style of a completely different image, effectively transferring the style of the second image to the first. The resulting image of the combined content and style is referred to as the target image. This technique can have fascinating results and is capable of producing new images that are very difficult to produce manually. This figure shows the process of style transfer in action. Of the 6 images in this figure, the top left image is the original image. The contents of this image are maintained. The remaining 5 images represent the obtained target images, as a result of combining the contents of the original image with the style found in the respective smaller images found next to each target image. As you can see, the results are truly astonishing, as each style gives the original image an entirely new look. It really goes to show that the style components of an image, such as color or texture, can really shape the final appearance of the image, as in all these cases, the core content of the image stays the same. Having learned briefly about the process of style transfer, let's move on to the code that is required to make it all happen. A big thank you to Udacity for providing this code, which is inspired by the paper Image Style Transfer Using Convolutional Neural Networks. The paper goes into full depth and gives detailed explanations of exactly what is going on through the process of style transfer. I highly recommend the read, as it gives insights into the logic behind the model that is used and also provides mathematical reasoning for just how style transfer is achieved. You can find this paper in the resources article prior to this lecture. As mentioned earlier, we will once again use transfer learning to load a pre-trained model to achieve this complex task. This will be seen later in the code. But first off, we are going to begin this Google Colab worksheet. I already named mine style transfer, and as we have previously done, we will install pip install torch and torch vision. And we will also need to pip install pillow version 4. As we have done before, we run this cell and install the required libraries, and I will see you in a bit. Alright, now on a new cell, we can import the same libraries we just installed, along with some others. We begin by writing matplotlib inline. As we will be making use of a lot of plots, this statement simply ensures that our plots and images display properly on the Colab workbook. And next we will import torch, as well as torch.optim as optim. You already know what that does, simply to make use of the atom optimizer. And now from torch vision, we want to import the transforms and models packages. Transforms you've already seen, simply allowing us to deal with image transformations in PyTorch, while the models will allow us to import a pre-trained model into our Colab notebook. And now from pillow, we want to import the image module, which will once again allow us to import and open the images that we want to work with. And now finally, we will import matplotlib.pyplot as plt, alongside importing numpy as np. These libraries are pretty standard, and you should be quite familiar with them by now. As mentioned earlier, we will be loading and implementing a pre-trained model, as we did in the transfer learning portion of this course. Style transfer is a complex technique that requires a powerful model. Models large enough to achieve this task can take very long to train, and require extremely large datasets to do so. For this reason, we will import a pre-trained model and take advantage of the sophisticated training it has gone through. We need a model that is very effective at feature extraction from images. The model in question here is referred to as the VGG-19 model, which is similar to the VGG-16 used in the transfer learning section earlier. The two models are compared in the following figure. The VGG-19 model is a bit larger, containing 3 more convolutional layers. In terms of the architecture of the VGG-19 model, the green and yellow portion seen in the image here is referred to as the feature portion, as it deals with extracting relevant features from the images that it receives, while the purple section is referred to as the classifier portion, as it deals with the classification of data. I've already explained to you the various distinctions between feature extraction and classification in the convolutional neural network section of this course. The same concepts apply here, except instead of building our own convolutional network from scratch, for this particular project, we will once again be relying on the pre-trained features portion of the model only. As such, we will only import the features of the model. This is done using the model.vgg19 command with an argument of pre-trained is equal to true, as we want the pre-trained weights that accompany the VGG19 model. Let's finish this command off with .features, as we only require the features portion of this model. Alright, and we will store this value into a variable that we will call VGG. And now, as we want to keep the parameters of the section that we imported constant, we will run through a loop of all of our parameters. For param in VGG.parameters, and we are going to use the param.requires_grad function with false as the argument. Don't forget an extra underscore over here. We do this to maintain the parameters constant. Setting this as false leaves these parameters unaffected by the backpropagation process that normally updates these weights. Alright, and now what we can do is on a new cell, we use the same. We have made a mistake. Name model is not defined, and that is because we imported models, not model. Trying that again. We should be good to go, and as the download progresses, I will pause this video and fast forward. Alright guys, welcome back. That didn't take as long as I expected it to, and once again we will use the same torch.device command as we've done in the earlier sections, and we can implement an if statement to use GPU if a GPU is available. Otherwise, the model will use a standard CPU. So we write CUDA, and now if torch.CUDA.is available, else we simply make use of CPU. Alright, we once again store this function into a variable that we will call device, and now we can attach our VGG model to our device variable and ensure that our model uses GPU whenever possible. And by running this cell, what it does is it outputs the architecture of our VGG variable. As we only imported the features portion of the VGG19 model, we only see a summary of that portion of the model. For this reason, the fully connected layers are not listed. The convolutional layers can be seen here. The input layer takes a 3-channel colored image, as we are going to be using color RGB images. The model then follows through with a total of 16 convolutional layers, as the remaining 3 layers in the VGG19 model are then fully connected classifying layers. There are also a total of 5 max pooling layers if you were to count them, as seen in the architecture figure shown earlier. Alright, and now that we've effectively imported our model and we've frozen the relevant parameters such that they are not updated during the backpropagation process, we will proceed to loading our images in the next video. I will see you then, guys.